Okay, this is a video about biased random walkers by Conrad Sircon. And so we've looked at the cases of random walkers as well as discipline walkers. And by looking at the example of a biased random walker problem, we're going to be able to combine the elements of both discipline and random walkers and be able to derive a diffusion advection equation by the end. So what makes biased random walkers different than the cases we considered before is that there are unequal probabilities of moving to the left and the right, hence the name biased in the title. And so the probability of moving to the left, for example, in this case is some number alpha, and the probability of moving to the right is 1 minus alpha. And as you can see, the two probabilities add up to 1. And so what we're interested in is to solve the equation, the probability of a walker at position I, as reflected by the x number scale, at time n plus 1. And so we can actually characterize this as as alpha times the probability of I plus 1, of a walker being at position I plus 1 at time n, plus 1 minus alpha times the probability of a walker being at position I minus 1 at time n. And so we want to take this equation and put it in such a form such that we can use Taylor expansion and be able to get our final equation, or an equation that has both diffusion and advection elements. And so we're gonna transform this equation. And I'm gonna erase it just to give myself a little bit more space into one that can be Taylor expanded. And we're going to utilize two new variables. One is going to be tau, which represents a very small difference in the time axis. And we're also going to introduce the variable a, which is a small change in x, right? So it's a small change in x. And this is a small change in t. So that's not int, that's in t. So using this information, we're going to be able to come up with the equation we had over here as the probability of x t plus tau, so at the next time step, right, a small move of the time step, is equal to alpha times the probability of x plus a and t plus 1 minus alpha times the probability of x minus a and t. So now, given this equation, we can actually Taylor expand it. So we Taylor expand the left, and here we're going to do it with respect to the variable t. We're going to get the probability of x, or p of x plus t, x and t, plus tau of p of t. So the partial time derivative of p of x and t, plus tau squared over 2 of p, sorry, this is a little crooked, so I'm going to work on this again. So plus tau squared over 2 of x and t, plus dot, right? Because there are more partial derivatives if you Taylor expand. But what we actually know is that since we're looking at this on a relative scale, we can cross this out as well as every other term as negligible. And so I'm going to do just that. And so now we're left with just this. And so we can now equate it to the right side. And so now we're going to have to Taylor expand both these terms. And so the first term is going to look like this. So it's going to be alpha of p of xt plus a of the x derivative of p of xt plus a squared over 2 of p, the double x derivative, right? And on and on and on. We're going to do the same thing to the other term. So now we do plus 1 minus alpha. Let me just write this a little bit to the left. So now we have both these terms. We're going to do the same Taylor expansion. So we're going to have p of x and t. Here we're going to have a minus a of p of x and t. And then this is going to be plus a squared. I realize this is a little bit crooked right here, so I'm going to correct that. P of x of x and t plus dot, right? And so we have the same thing here. So the first thing we should be able to see actually is that the p of x and t on each side actually cancels out. And the reason that's possible is, so here we've just got a p of x and t. Here we have an alpha times p of x and t. And here we have a 1 minus alpha of p of x and t. And as we previously noted, alpha plus 1 minus alpha is just equal to 1. So it's as if we have p of x of t, just one p of x of t on here, and we have one on here. So we can actually go ahead and cross these terms out as canceling. And so now what we're left with is we've got this on this side. And I'm actually going to move this down here to give us a little bit more space so it's a little clearer. And it's equal to alpha of a p of x and t plus a squared over 2. Okay, so we're running out of room here. This is a bit of a problem. So I'm going to rewrite that again. I'm going to go all the way to the bottom. So once again, we've got tau of p sub t of x and t is equal to alpha a of p x of x and t plus alpha a squared over 2 of p xx of x and t plus one minus alpha of a p x, just a single derivative, x derivative of p, plus 1 minus alpha of a squared over 2 of p xx x of t. Okay. So I'm going to erase this top line and then move our next calculations up there. And so what we're going to get up here